thanks a lot, Cordian, and also, well, thank you really for giving me the chance of coming here. It's a big adventure for me being here, and also an honor, and I'm very happy to be able to share these thoughts with you here today. So, well, as an initial disclaimer, my background is in physics, not in mathematics, but I'm interested in several aspects. Well, I care about what I will talk about today very much, as well as other things. These things have to do with understanding the reach of universality. And I'll try to explain what I mean by universality, but that is in fact a large part of the question. What does universal mean? As well as the reach of undecidability. And I'll also try to explain the relation between the two. But let me start with universality. And I want to start with an example. So that's a bit of a historical evolution of how I came to investigate these questions, which has to do with spin models. I will define in a second what they are. For the moment, think of them as toy models for complex systems. And what we found is that some simple spin models, or that look simple, like the 2D Ising model with fields, can simulate any other spin model. And that includes models with, I'm not sure if I have a pointer. It's pretty weak. But on like high, so where the spins are not two-dimensional, they are not like two-level systems, but they are like Q-level systems, or where you have like many body interactions, like 4 body interactions. Here you only have 2 body interactions, or where you have your spin model placed on a higher dimensional lattice, or it could be a graph. So any sort of geometry or graph, yeah, and any such thing is valid. And in this sense, we call the model on the left-hand side universal. And I'd like to explain this example to you first so that you see what's on my mind and why I want to relate it to other well-understood forms of universality. So a classical spin model, what is it? OK, so for a moment, the spin is just a discrete and classical value, like taken from a finite alphabet, 0, 1, say. And the Hamiltonian is just a cost function, as in a map from spin configurations to energies, or a family of cost functions. I will distinguish the 2 cases. And in fact, physicists are often not very clear about which of the 2 they mean. When they say the Ising model, it's unclear whether it's for a fixed system size or it's not. Okay, but I'll try to distinguish these things. Typically, there's a local structure, as in local Hamiltonians. And that's going to be important at the end of the talk, because I see this local structure as a grammar of physical interactions. And maybe if we think about computation, the grammar are the transition rules of the automaton that's recognizing the language. But for the moment, the local structure is not important. You can just think of it as a cost function. Okay? Cost function means a function. But typically, you want to optimize this function, so people call it a cost function. So the paradigmatic spin model is the Ising model. And just to set some very basic notation, it's all classical, by the way, although many of the things I will say also apply at the quantum level, but I'm still at the classical level. I'm trying to understand first the classical level. So in this Ising model, you have some so-called spins, which are variables which can take values plus or minus 1. You multiply them, so you have like a parity function. If they are both in the same direction, then you get a +1. If they are in opposite directions, you get a -1. You have a minus sign in front, so typically you want to get them aligned if this thing is positive. And then you have some coupling strengths. So here they are unfixed, this Jij. Also unclear from what's said. Physicists take them from the reals, but if you want to make a connection to computer science, they should admit a finite description. And these were invented to understand magnetism, or in a very simplified way, by Ising and by Lenz. And you can imagine like this spin as describing the spin of the last electron in a solid. But of course, this is now think of them just as discrete classical variables. So they can stand for anything. For instance, so that's why they are useful as complex models for toy models for complex systems. For instance, a gas, well, you can kind of discretize space into cells and say that in every cell, either a molecule of gas is present or absent. That's a two-level variable that you can model with an Ising model. That's called the lattice gas model. Or in artificial neural networks, of course. They largely use Ising models, and the two values stand for whether the neuron is firing or is not. In knot theory, to my knowledge, the Jones polynomial can be written as the partition function of the Potts model in a certain parameter regime, and the Potts model is a generalization of the Ising model. There are several generalizations. That's one of the most popular ones. In protein folding, the local variable is not two-level, but rather 20 levels, and these are like the amino acids in a given position, or 21 if you also want to model the absence of an amino acid in that position. And that's one of the approaches that were proposed to understand, for example, aspects of the three-dimensional structure of proteins. In ecology, people would care about things like, I don't know, the size of canopy trees seen from the sky. And if you see that as a spin model or as an Ising model particularly, then, well, many things are at criticality. I think that's kind of one of the lessons of several aspects of complex systems, that very often things are at criticality. Or in random language models, I think the spin there is modeling whether there is a change in the grammatical rule or not. There are many more. There's even, urban segregation, many more things, okay? But I'm trying to give you a picture that they are, you can do many things with them. Why? Why are they so expressive? I really wonder, why can you do so much with so little? It need not be the case. I mean, why? And I think that perhaps one of the reasons, or one of the ways to understand that, is because they are universal, particularly because the Ising model is universal. Namely, it can simulate any other spin model. And that's what I'd like to share with you now.
Universal in a class of spin models, or in a class of computing like Turing computers?
Thanks for the question. None of the two. I will define it now. So it applies to all spin models. So it's not only for a so-called universality class, if that's what you meant. And it's also not Turing computable as far as I see it right now. It seems to be a weaker form of universality, and that's precisely what I'm trying to understand. Okay, so let me define this precisely. And I need to go through the definition so that you can, maybe you can tell me what is really going on, okay? So first of all, a spin system is a function from a given number of spins to energies. So it has a finite domain. It's a given number of spins, n. A spin model is going to be a family of such spin systems. For example, the 2D Ising with fields, with inhomogeneous couplings and fields, is going to be the family of such Hamiltonians so these are inhomogeneous couplings and magnetic fields. And so these are free, like, right? They both run through some, they need to admit a finite description, whatever, the computable reals, the integer, or something like that. And say that this graph is a two-dimensional lattice of any size. So I will denote such family with an index alpha. This alpha contains all the information about the magnetic fields, the coupling strengths, and the size. Okay, now this is the relation between spin models that is going to be important. Okay, so I say that a spin model, this family, simulates a spin system H prime if for any threshold delta, that's going to be like, delta should be an energy, there is an alpha, so there's an element in the family, so that, in essence, H alpha mimics the behavior of H prime. Or a little more precisely, the low energy sector of H alpha equals the full energy sector of H prime. So a bit more precisely, we have 4 requirements. First, the energies of H alpha and H prime are identical, potentially up to a constant multiplicity in the energies of H prime. So maybe each level here is multiplied, or it has a multiplicity m, but this m needs to be the same for all levels. the states of a subset of spins of H alpha, called the physical spins, are in one-to-one correspondence with the states of H alpha, H prime. So you can look at the physical spins and think of them as the eigenstates of H prime. By the way, everything is classical, so I talk about eigenstates and spectrum. It's trivial, right? In this case, it's just a function. But, well, this also applies quantumly, and I come from quantum, and I'm used to this kind of words. But it's just a spin. It's just an element of the n-fold, like Cartesian product of a finite alphabet. Okay, and the partition functions coincide up to a constant factor and some error. So that's important if you want to claim that you're reproducing some thermodynamical properties. And the description of H alpha is polynomially larger than the description of H prime.
I mean, only polynomial.
At most.
No more than polynomial.
Yeah, at most, yeah. And a spin model is universal if it can simulate any spin system. Okay. Now, theorem, that's the full characterization. It says a spin model is universal if and only if its ground state energy problem admits a polynomial time faithful reduction from SAT. I'm going to explain that right now. And moreover, it is closed. I'm going to explain that right now. I first wanted to announce the result. It's coming, I promise, in 30 seconds. So first of all, the ground state energy problem of a spin model is identified with a set of yes instances to the question, given an element of this spin model, an alpha, and a k, which should be, it's like an energy, so in the same set of where the energies are. Does H alpha have a spin configuration with energy below k? So that's a decision problem, yes or no. And it's naturally in NP. And for some fairly simple models, it's already NP complete. Now, moreover, we require that this faithful reduction be faithful, meaning that there is a map that, for yes instances, maps a witness of SAT to a witness of GSE. Now, Avi was calling witnesses proofs. That's exactly the same thing. It's the thing provided by the wizard to the king. That testifies, that certifies, sometimes it's also called a certificate, that certifies that your instance is an element of the language. Okay. So we require that the reduction also behaves nicely or preserves somehow the structure of the witnesses. For most of the NP completeness results I've seen, all but one, the reductions are faithful, but of course we need to explicitly require that. And closure.
Could you remind us what SAT means?
Oh yeah, I'm so sorry. SAT is satisfiability, and it is defined as follows. Given a Boolean formula, does it have a satisfying assignment? And so it's a decision problem. The answer is yes or no. And well, if it is yes, then there's a natural witness, which is the satisfying assignment. And if the answer is no, there is no witness. So that's the soundness part. And every Boolean formula can be put in like 3 conjunctive normal form, which means as a conjunction of clauses such that in each clause you have a disjunction. And it is kind of well known that if you have clauses with just 2 literals, like 2 Boolean variables, so that's called 2-SAT, when you have it in conjunctive normal form, then that's easily solvable. That's in P. But 3-SAT is NP complete. And that's really wonderful. Like there's a very sharp transition, which happens very early, like from 2 to 3. I mean, and it's really insightful, I think, the fact that 3-SAT can capture the complexity of K-SAT. Okay, maybe it's trivial. I mean, it's a very well-known fact, but I like the proof. You can make a reduction from K-SAT to 3-SAT. And it's kind of telling you that 3 is as complicated as it gets, given all the premises of what goes on in computational complexity, right? That, like in a reduction, yeah, the image is non-surjective, so you're using like auxiliary variables to simulate the effect of the K variables in K-SAT. But I think the moral of the story is quite similar to some things that are happening here. In fact, I think that NP completeness is a form of universality, as I will talk about later, or mention later. Yeah, so a spin model, this family is closed if for any 2 elements in the family, you can, there exists a third element, gamma, so that H gamma simulates the sum of the previous 2 elements. And so I'm not being very careful about what's happening with the domains, but really the interesting thing is that the domains of H alpha and H beta may partially overlap and partially coincide. And so it's not obvious that, that H gamma, so first of all, it's not obvious that H alpha plus H beta it need not be in the model, but we say that the model is closed if there's a third one that can simulate it. So it's some sort of a modularity condition on the family. And well, Theorem, the 2D Ising model with fields with inhomogeneous couplings is universal. And by extension, anything that's more complicated than that is also universal. And so in plain words, essentially every spin model is universal. Essentially every spin model that's not too simple, that is not kind of hasn't crossed this threshold of admitting, like the first condition is pretty mild. The second one, it's a bit unclear. It's something we defined and we don't really know. But I think both are fairly simple. And so we find that essentially everything is universal. So essentially everything is as complex as it gets if it is given the power of additional variables and tunable parameters. OK, and I'd like to give you a sense of the proof of this direction, because that is where what is happening is what I'd like to understand. OK, so this is the interesting direction, namely that these 2 things suffice for the spin model to be universal. And it goes as follows. So this is going to be only slightly technical, and in the next slide, I will give a summary in plain words. OK, how do we do that? OK, well, take a spin system, which is just a function from a finite alphabet to the n to, say, z. Z are the energies. Now, for every spin configuration in sigma n, consider its characteristic function. I'm not sure if it's called like that. It's a function E sigma, so that when evaluated on sigma, it's 1, and when evaluated on anything else, it's 0. Construct the Boolean formula phi sigma on a bunch of Boolean variables x and a so-called flag spin, f sub sigma. And this Boolean formula, I tell you from the beginning, is satisfiable. So what is interesting is not the question whether it is satisfiable or not. It is the fact that the satisfying assignments are those where the flag spin is precisely the characteristic function of x. As in, there is some computation, you see, in the satisfying assignments of this Boolean formula. In the satisfying assignments, the flag spin is correct. It is 0 if the first ones are not sigma. It is 1 if the first are sigma. Now, apply the assumption, faithfully reduce the satisfiability of this Boolean formula to the ground state energy problem of the spin model. And this gives you an element of your spin model. So instead of H alpha, I'm calling it H sigma. The ground state of this H sigma has the property that the flag spins are correct.
How do you know you can get a Boolean formula like that?
You can construct it easily. So, for example, yeah. So it's all finite and it's all very well behaved. I don't know, you can construct it easily. So you want to tell whether your 2 spins are 0, 0. Then you construct a formula set with 3 spins, because you have the 2 first spins x and the flag spin, with the following satisfying assignments: 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 0. And so, in particular, if you do it in conjunctive normal form, you need to put a clause that kills every other formula. So it's, yeah, you can construct it. OK, so now, what do you do? Now, you're sure that in the ground state of the spin model, the computation is correct. The computation of the flag spin is correct. So what do? You lift the energy of all other of all excited states to above delta. Remember that delta is that threshold. And you don't want to look at what happens over delta. That's like garbage. Okay? Yeah. And yeah, that's what I just said. And then finally, tune the energy of this local flux spin so that when the flux spin is in 0, its energy is 0. But when the flux spin is 1, the energy is precisely h prime sigma. That's the energy of the target model, of the target spin system in state sigma. Okay, and do this for every element of the domain, sigma for every spin configuration, and now add the Hamiltonians using closure. Okay, I'm sorry if this was a little bit too detailed, but the summary is that you are doing two things. On the one hand, you're encoding the computation of the characteristic function in the ground state of the spin model. This you can do because of NP completeness of the ground state energy problem. But for this form of universality, that is not enough, because that would only allow you to reproduce the behavior of the target spin system for one spin configuration. You need to mimic the entire spectrum. And that you can do with closure. So now, is this exclusive to spin models, or what's going on? Or is this some veiled form of Turing universality? Or is it some other well-known mathematical structure like the basis of a vector space? So I would like to understand these questions because I think they would allow us to transfer a lot of results among disciplines. And that's kind of the goal. In particular, let me show you some similarities with other forms of universality. Okay, so for spin models, we have just seen that if you have a target spin model, which is like defined on a hypergraph or whatever with crazy interactions, that can be mimicked by a 2D Ising model with fields. At the price of introducing additional variables, these are here denoted in gray. That's the map to the universal model. You have actual and auxiliary variables, as in physical and auxiliary. And the description of the original model takes the form of the pattern of coupling strengths and spin configurations that you plug in your 2D Ising model. That is the program, if you want. That is telling the 2D Ising model with fields which spin system it has to simulate. Okay, in computer science, a priori, say that you have a Turing machine, a set of transition rules, and well, you can input elements from a finite Clint star of a finite alphabet, and then it gives you an answer. But now, this can be transformed into something happening for this universal Turing machine as follows. You need to input a description of the algorithm it is supposed to simulate as part of the input. This is here the key step, the key idea. You thought that these two things were at different levels, right? The algorithm, as in the set of transition rules, and the data, they seem to be at different levels, but they are not. Like, at least for Turing machines, for linear bounded automata, I think they are. But yeah, they are not. So there's a confusion of levels, which gives rise to universality. I think this is the magic here. So you can input a description of the algorithm as part of the input, and then this fixed universal Turing machine will behave like it. So so the analog of physical and auxiliary spins is played by the input versus the description of T. So you also need an enlarged input in order for this trick to work. For this thing to be true, right? You need to input more bits of data. Very much like here, you need to have auxiliary spins. Yeah, and the description of the model is, of course, of the target model is the part of the input describing T. Okay, now in neural networks, there's a similar form of universality. In this case, I think you want to learn a continuous function or something, like a function from some nice set. And there is a so-called universal approximation theorem that says that for a feed-forward neural network with a single hidden layer, with an unbounded number of layers, units, for any function in that set, an epsilon, there is a feed-forward neural network with enough hidden units, so this unit in the middle, and a choice of parameters, so that the function implemented at the visible level here is epsilon close to your target function. Okay. And remember that these things are spin models in essence. They look at maybe slightly different things than what we've been looking at so far, but they are spin models. And so here they call these things visible and hidden units, but it's essentially the same thing. And the program, as in the description of F, is going to be in the distribution of weight and biases and the size of the hidden layer. And a similar result holds for restricted Boltzmann machines. Okay, so these things look similar. Are they actually similar? Or are there formal connections? Can we prove theorems that says, if you're universal in this sense, maybe you are universal in this sense, or in that other sense, and what does this imply? Or what are we to do of the full characterization of universality here, for example? That is what I would like to understand. So, another way of expressing that is that I'd like to understand the reach of universality, as in how far it goes, in how many places, in how many different ways can it be instantiated, and what are its consequences, as well as that of undecidability, which I see as intimately connected. And I'll try to share with you my intuitive argument and some preliminary formal results that we have in making this connection precise. But yeah, I kind of see them as two sides of the same coin. How? How can we tackle this goal? Okay. I propose to do so like in these two ways. One is by proposing a framework for universality. And so that's kind of a top-down approach. And the second one is by comparing two examples, spin models and Turing machines, comparing them really well and seeing what's going on there. That's a bottom-up approach. And somewhere in the middle, I will tell you about the relation to undecidability. Okay, so the framework for universality. Actually, I believe we need to do that in two different ways. One is conceptually, and the other is categorical, or like formally. In particular, we use some basic category theory, but I just mean formally. Okay.
Can you say intuitively, very short, why does undecidability come from universality?
Yes, because universality allows for self-reference. So if it can simulate any other thing, it can in particular simulate itself in a non-trivial way. And as far as I see, undecidability is about self-reference and negation. So whenever you have self-reference, you're very close. Typically, you're expressive enough also to do negation, and then you can do self-reference and negation. And that is, for example, the case with Turing machines and the halting problem. The standard proof of the halting problem says, assume a machine existed that would solve the halting problem, then feed it its own code, self-reference, and negate the result. As in, if the first halted, the second is not going to halt, and then you reach a contradiction. And in this case, what you conclude is the machine you assumed existed in the first place cannot exist. Okay. So let me start with this conceptual framework for universality. Okay, I think this part is pretty difficult, at least for me, because it's pretty hard to set the boundaries of because it's a top-down approach. So yeah, but okay. So of course, this starts with this question: what does universal mean? Okay. So of course, this question brings us to the realm of natural languages and meaning, and we are outside the easier world of formalizable things. And okay, a priori, it means relative to the universe. And by extension, this is if you want a frozen metaphor, I really like this expression, it means all-encompassing. Okay? So, yeah. So that's my working definition. And now all refers to a collection that you're going to quantify. And encompassing refers to a relation. And so what we call the basic structure of universality says this: given a collection C and a relation R that lands in C, which just means that the second argument of R is in C, U is universal if U, C is in the relation for all C in C. Okay. So universal is relative to a collection and a relation. And I'm not saying anything about U could be in the set or not. R, this relation need not be anything transitive or reflexive or anything. The set could be finite or not. I think this is the bare minimum structure that we need. Okay, so let's see how this relation is instantiated in many different concepts that we know. Okay, of course, the first one is going to be computation. In a universal Turing machine, C is the collection of Turing machines, R is simulation, and U is a universal Turing machine. The second one is completeness in a complexity class, like NP completeness or RE completeness, or well, in this case, C is the collection of problems in that class. R is a meaningful form of reduction. So for NP completeness, you need polynomial time reductions. For RE completeness, you need computable reductions. And U is a complete problem. It has the same structure. But there's also the universal gate set. In this case, C is the collection of Boolean functions. And C is the relation that says that, well, there exists a sequence of gates from my universal gate set that I can apply so that the result will be identical to my Boolean function. Okay. So the relation is a bit different. There is this additional, there exists a sequence.
What's a gate?
Oh, a gate is a Boolean transformation, like not, or like and, or like fan out. For quantum computation, universal gate set is a little different. So C is the set of unitaries of arbitrary size. R is the relation that says for every epsilon, there is a sequence of gates in U, which is epsilon close to C. And U is a universal gate set. Of course, these measures of epsilon close will depend on the details. There are theorems saying how they can be, but that's in essence, again, the relation. In physics, people think about universality, they often think about universality classes, where in this case, C is the collection of Hamiltonians, of all spin Hamiltonians. And the relation says that C flows under renormalization into one of the fixed points, like U, and U would be the set of fixed points. And then there's ours, which has also been generalized to the quantum case. So yeah, I think in ours, like these universal quantum spin models, C would be the collection of quantum spin systems. The relation expresses simulation, which is defined differently in the two papers, and U would be a quantum or non-quantum universal spin model. Okay? It's another relation, and a priori it's not obvious how they are related. Feed-forward neural networks, we have similar things. C is the set of continuous functions. Yeah, that's what I explained earlier. R is this relation that there exists. For any epsilon, there exists an element so that the visible units are epsilon close to that element. And U would be the set of feed-forward neural networks with one hidden layer. Similarly for restricted Boltzmann machines. In this case, you want to approximate discrete probability distributions. And the details on the epsilon measure, like the distance measure, will vary, but because it's a statement of denseness in, yeah. Okay, now in mathematics, well, the basis of a vector space, or a generating set for a vector space. So C is a vector space. The relation is linear combination, and U is universal if it contains a basis. Or the extremal point of a convex set. Well, C is a convex set or a convex cone. The relation expresses convex combination. And U is universal if it contains the set of extremal points. or extremal rays for the cone. Okay, there are also things called universal graphs. I know next to nothing about them, but I think the definition literally instantiates our basic structure. So C, for example, could be a set of graphs of any size. The relation would say it is a minor or some other, or a subgraph, and U would be the universal graph. There's also something called the universal differential equation. It's a statement of denseness again. So it says that, so C would be a set of continuous functions, and the relation expresses that for an epsilon, there's a solution to your differential equation, which is epsilon close to that.
Does that exist?
Yeah, it exists. There are like 3 or so. If you Google that on MathWorld, you will end up in an article that gives you the universal differential equation, and then there's another paper with 2 more. Yeah. I don't know why. Well, I probably, like, I wasn't able to understand it, but yeah. Okay, this example actually is for Avi. Maybe he's not here, but because he mentioned biology several times, it's interesting that some people are trying to think about the origins of life, or like how to define life in a way that's independent of the life we see on Earth. And they want to propose this thing called universal biology, which doesn't exist. But what's interesting is that they are inspired by Turing and by universal Turing machines. And they say that they have to solve the opposite problem of Turing and the other thinkers 100 years ago, in the sense that we have one very prominent instantiation of life, namely the biosphere, but they want to come up with an abstract model of life, right? Which, of course, potentially would describe life in other planets and other forms of life and so on. And which is kind of the opposite of what thinkers were facing like 100 years ago when they had to ask, when they asked, what is a computer? What does it mean to compute? Which I think is a really difficult question. Yeah, I thought that was interesting. Okay, that's a good example, the universal grammar. In this case, so in the sense of Chomsky, in this case, C is a collection of grammars of natural languages. The relation expresses that there's a choice of parameters of U, after which it becomes C, and U is a universal grammar, which is actually a meta-grammar, not really a grammar itself. Okay, and now this is maybe one of my favorite examples. In philosophy, there's something called the problem of universals. It's a very old problem in metaphysics, which tries to address the question, how is it possible that we assign the same attribute to different particulars? By virtue of what? What is the relation between these particulars? Like, why can you say that 2 things are red or round? Because this relation is not physical. And then Plato and Aristotle and others said, well, actually, this is the case because they are both instantiations of a so-called universal that lives in another world. It doesn't live in this physical world, lives outside of space and time, and it's immutable, and so on. And then the others, like nominalists, like Occam and others, say, no, there's no such thing as universals, and then they run into all sorts of problems. Okay, of course, the universals, well, C is the collection of all particulars sharing an attribute. The relation says it is instantiating that universal, and U is the universal thing. Now, what's particularly interesting here is that one of the main challenges the metaphysical realists face is the attribute is non-self-instantiating, which is, I am a liar. It's the self-reference and negation. And of course, it's problematic. And so I think that this basic tension between universality and undecidability that I'm trying to understand is also present in this problem in metaphysics. And in my dreams, we may be able to say maybe something interesting, or by making this connection, I don't know. Okay, what do we do with this exercise? Well, we try to then classify types of universalities. For example, we try to say, which of these notions of universality is related to undecidability? Well, yes, the Turing machines, the problem of universals, no. The universal grammar, the basis of a vector space, extremal points, as far as I know. And also, I see universality as some sort of an generation of complexity. Or I would like to understand why everything is so complicated, or some aspect of that. in the light of universality, like because very simple things are universal and are capable of capturing the complexity of everything else somehow. And so, yeah, so I would claim that Turing machines and spin models do onset the generation of complexity, but the universal grammar doesn't, or the problem of universals doesn't either. This is something like what David Deutsch calls the jump to universality in his book, The Beginning of Infinity, if you've read it. Yeah, and maybe, can there be a full classification? Can there be a universal framework for universality? And I think the answer is no, because of the basic tension with undecidability. And okay, I'll try to explain that. Okay, how am I doing? I'm not doing well, right? 10 minutes. Okay, so now I'd like to be slightly more formal and share with you how we are trying to formalize these ideas. So yeah, we're doing this with category theory. I hope it's the right choice. So we have a basic object called a simulator, which is a map from something called programs. So you're supposed to read this from bottom to top. So it's a map from programs and a context. It's a map that splits in this way with something we call a compiler and a context reduction. And it ends up in this we call this things, and C is again the context. And on top of that, there's going to be a map that we call eval, which results in some sort of behaviors. Okay. And we say a simulator is universally for everything T. There is a program P, such that for any context C, the evaluation of SPC equals that of TC. In other words, SPC behaves like or mimics TC, the thing itself, for any context. Okay, I mean, what's interesting is the instantiations now. Yeah, and we also relate such simulators and then grade universality as in saying this is stronger than that one. Okay, so for a universal Turing machine, P is the set of programs, the context is the inputs to the computation, T is a singleton, can be a singleton, the universal Turing machine. Now this function, this should be here, SC, no, because these are pairs. Pairs, this is a pair of a program with an input, right? This is here, this magic happening, that the fact that the program becomes part of the context, becomes part of the input. And this is the output to the computation. For a spin model, this would be all spin systems. This would transform the spin system to an element of the spin model. This would be the spin model. These are the spin configurations. This gives the spin configuration of the spin model. And finally, the behavior are the energies. And it's also universal according to this framework. But also things like a dense subset are universal. In this case here, you have a singleton. The programs are irrational in a precision. This gives us an inclusion of the rationals into the reals. Here we have this thing. And finally, this eval maps T comma delta, so the real and a precision to an open ball around number T. And then the statement that the rationals are dense in the reals is the statement that the simulator is universal. In some sense, the rational is like the program. Okay, now that's what I try to make a little bit precise, the relation to undecidability. Okay, so, I need a little definition here. So take a map from A cross B to C. Okay, in principle, this is in category theory, and then these are like objects in the category, but this is not so important now. And we say that such a map is weakly pointer-ejective if for any G that goes from B to C, there is an A in the first thing, such that f of A running over all inputs here, all B's, equals G of running over all inputs. So some other people call this, if this is the case, then they say that F represents G, right? Because F has an enlarged domain, and you can pick an element of this enlarged domain, as in A, so that in the rest of the domain, F behaves like G. Okay, this is what some people call weakly point surjective. Now, Lovier's theorem, which from the 60s, says that let a function be weakly point surjective, then every g has a fixed point. So if the function is weakly point surjective, then g cannot be too general. In particular, it needs to have a fixed point. And this is to avoid contradictions, in my words. So another way to express it, like the contrapositive form, would be saying that if there is a g which does not have a fixed point, like negation, then f cannot be weakly point surjective. As in, it cannot represent all functions. And so for me, is that this idea of this form of surjectivity feels like, or it should be, universality. It's kind of like universality. And the limitations imposed by Lovier's theorem are like undecidability. And so I think that is what we have to try to understand to make precise the relation between the two. And so what's interesting is that if you look at linear bounded automata, where I'll get to in a second, which are like a weaker form than Turing machines, weaker form of automata, we showed that eval cannot be weakly point surjective. In other words, they don't have universal, there are no universal LBAs, and so they are not subject to undecidability. On the other hand, of course, for Turing machines, eval is weakly point surjective, so there are universal such things. But the price to pay is that you have fixed points. What are the fixed points? They are the undefined points, as in the non-halting points. So in other words, Turing machines only compute partial functions. So there's a trade-off here, I think. Okay. Okay, now comes my intuitive argument. So I take undecidability very broadly to mean that no system can talk about itself. So by system, take a set, and by talk, describes an attribute, which is, say, binary. So a map from the set 201, which can be identified with its extension. I don't know how you call it, like the set of elements where it is true, so which is an element of the power set. Like for finite sets, that would be the case. Okay, a set can never be put in one-to-one correspondence with its power set. And my way of understanding that is that, yeah, the liar paradox. So no matter how powerful your system is, how mega infinity it is, there's something which it will never be able to capture, which is the truth of the sentence, I am a liar. Yeah, the self-reference and negation will always escape the system. And so I think this is very powerful because it can be instantiated in many cases, like the sentence is false, a halting problem, Gödel's first incompleteness theorem, Russell's paradox and set theory, Tarski's theorem on the undefinability of truth, Cantor's theorem, and so on. And they are all incarnations of this liar paradox. And at the same time, it's very far-reaching. Because, of course, it means that if you take a set and take its power set, and it's the power set of the power set, this never stabilizes. So, for example, there are infinitely many types of infinity. And I think this is mind-blowing. And so my take-home message is the liar paradox cannot be fixed in a finite way. So for me, so therefore, it cannot be fixed, as far as I'm concerned. I may be wrong, but that's how I'm understanding this at the moment. Yeah, and can be made precise in Lovier's theorem. So all of these things up here follow from Lovier's theorem as well as others. And maybe I have a question for you, mathematicians. And I wonder if a proof which is not by contradiction can ever be so far-reaching. I just don't know.
There are too many knots there. What does that last thing mean?
Sorry? This thing?
It has too many knots for mine.
So it feels to me like that when you do a proof by contradiction, you say that something is not possible. But you leave open, you don't know how many possibilities of what is possible. So it feels to me like that's really powerful. And particularly self-reference and negation is a proof by contradiction. And so I wonder if a proof which is like a constructive proof, as in something that you can prove from this it follows that, and from that it follows this other thing, and so on, can ever be so far-reaching. I feel that this proof is very far-reaching. It's very simple and very far-reaching. And I wonder.
there is a gap between constructive proof and a proof by contradiction. So you want something which is not a proof by contradiction or something which is constructive?
I don't know. I don't know. I don't know. Let me see. I am just struck by how simple this proof is and how far-reaching it is. And I wonder if anything similar could ever be the case with a proof that maybe applies a set of transformation rules on your axioms and doesn't use the excluded middle. Doesn't use contradiction. Yeah, I just don't know. And maybe we can discuss this later because I'd be very interested in hearing your perspectives. Okay, yeah, that's the intuitive argument which I already gave. Universality allows for self-reference, which is a step away from self-reference and negation, which is at the core of undecidability. But of course, to make this precise, you first need to define universality, which is the first part of the talk. And clearly, there are some trivial forms of universality which are not going to be bound to undecidability. And I also see some kind of a fundamental tension between the two. Like universality tries to capture the complexity of the entire system, and undecidability says this will never be possible in a thorough way. Yeah, I'm not sure what to make of that. Yeah. Okay, and maybe I'll skip this entire section. Let me see. Okay. So sorry about that. Okay. So I'm trying to understand what's the scope of universality and undecidability, and we're trying to do so in two ways. One is by proposing a framework, conceptual and formal, for universality. The other is by comparing the two best understood examples where we have cast spin models as formal languages and classified them in the Chomsky hierarchy and seen that the universalities do not match. And yeah, that's all. Thanks.